Hey, PreCalc kids. Today we're looking at binomial expansion on PreCalc with Mr. Forbes. Notes out, and away we go. We're looking at the binomial theorem. The binomial theorem is a theorem that applies to binomial expansion. The reason we call it the binomial theorem is, look here, we're going to expand the binomial x plus y, and we're going to see what happens. For example, for n equals 0, what is the exponent for x plus y to the 0th power? Well, that's nothing. That's 1. So it's 1, x to the 0, y to the 0. If we let x plus y to the first power, that gets us 1x to the first plus 1y to the first. I am going to write all of the coefficients and exponents just so we can see the patterns that are going to come when we fill those out here in a second. What if we look at x plus y quantity squared? Well, that's just FOIL. We get 1x squared plus 2xy plus 1y squared. What if we multiply that by another xy and we get xy cubed? Well, here's where we're going to start looking for patterns. We're going to get 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. Next, x plus y to the 4th. We're going to get 1x to the 4th plus 4x cubed, x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the 4th. And we're going to stop with x plus y to the 5th and see what patterns we can see. We get 1x to the 5th plus 5x to the 4th y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the 4th plus 1y to the 5th. This is what's called Pascal's triangle. And he did a lot of work with this back in the 1700s. Pascal is a famous mathematician. There's some patterns that we notice that come out of this. The first thing you'll notice is whatever n is, that binomial expansion has n plus 1 terms. For example, n is 0, we have 1 term. It's just 1, but it is 1 term. 1 has 2 terms, 2 has 3 terms, 3 has 4 terms. So the first thing we notice is x plus y to the n has n plus 1 terms. So if we did n to the 10th, there would be 11 terms. Note the first term is x to the n. The last term is y to the n. So the starting and ending exponent is the same as the power of n for our binomial expansion. Number 3, notice we go from x to the 4th, x cubed, x squared, x, no x. We start with no y, 1y, y squared, y cubed, y 4th. So the x's keep going down by 1s. The y's keep going up by 1. We're going to say that as this. Each successive term the x exponent subtracts 1. The y exponent adds 1. What else do we know? Let's look at x to the 5th. Well, if we look at all of the variables exponents, what happens? X to the 5th, that's 5. 5 plus 1, or 4 plus 1, sorry, for the exponents, that's 5. 3 plus 2, that's 5. 2 plus 3, that's 5. 1 plus 4, that's 5. 5 is 5. So the addition of the exponents is always the same as n. So in each term, the sum of the exponents is equal to n. In number 5, this is probably the hardest one to really see the pattern, but once you get it, it makes sense. And it can actually help you derive the whole sequence using this pattern. Here's the pattern. And let's look first at the n equals 4, and then we'll see again how it works in n equals 5. Notice, how do we get 4? Here's the pattern. I'm going to take the coefficient of the first term, multiply it by the x exponent, and then divide it by the position of that term in the polynomial. So my coefficient is 1. I'm going to multiply by the exponent 4. That's 4. Divided by the first term is 1. That gives me 4. I'm going to do the same thing. 4 times the exponent, 3. 4 times 3 is 12. This is the second term divided by 2. That's 6. What? I know. Amazing, right? 6 times 2 is 12. This is the third one. 12 divided by 3. There's the 4. Again, I know, right? 4 times 1 is 4. Divided by this is the fourth term. There's the 1. So there's the pattern that we can use to get the coefficients. Let's look at the same thing with n equals 5. The first coefficient is 1 times its exponent is 5. Divided by its position, the first position, 1. There's 5. 5 times the exponent 4 is 20. Divided by this is the second term. 20 divided by 2, there's 10. I know, mind-blowing. 10 times 3 is 30. Divided by the third, there's 10. 10 times 2 is 20. Divided by the fourth term, there's the 5. 5 times 1 is 5. Divided by the fifth term, there's the 1. So let's write that down as the rule. The coefficient times the x exponent divided by the number of term equals the next coefficient. So that can actually help us generate any n we wanted to using that pattern. And number 6, what else do you know? Well, there's a 1x to the 5th here. There's a 1y to the 5th here. There's a symmetric. So the triangle is symmetric. We're going to define that thing as Pascal's triangle, the coefficients of the array, x plus y to the n. So if we forget about the variables and we just look at the coefficients, we get 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, on and on. Again, there's a bunch of patterns that have been developed in that triangle as well that make for some interesting study as well. How do we use this? Well, again, we can use this as a pattern to do our expansion. Let's look at some examples. Example 1, letter A, use Pascal's triangle to expand each binomial. So now we're looking at x to the 5th. Again, let's walk through this without looking back at anything and just using the rules we talked about, how we would do this. Well, we know the first one is just going to be x to the 5th. We're going to use our pattern to generate our coefficients. So our coefficient is 1, times 5 is 5, divided by the first position is 5. The x exponent has to drop by 1, so it's a 4. And then we start adding the y. We're going to repeat that pattern. 5 times 4 is 20, divided by this is the second term, that's 10. We drop by 1 to get x cubed and add 1. Repeat the pattern. 10 times 3 is 30. This is the third term, that's 10. X drops by 1 to get squared. Y adds 1 to get cubed. 10 times 2 is 20, divided by 4, that's 5. X, now we drop by 1 to get 1. Y is 4. And we get 1y to the 5th. Again, we can check it because it has to be symmetric. So the 5 and the 5 match, the 10 and the 10 match, the exponents match. Although they switch variables, the exponents match all the way across there. Now, how are we going to do that with something like letter B? So now we don't have an x and y. Now we have some numbers. Well, the first thing we're going to do is we're going to use Pascal's triangle as our pattern. So we need to generate the 7th. And here we go. So this would be, we're going to do that same pattern. I'm not going to talk you through it. I'm actually just going to sketch this down. Remind me in class, and I'll show you another way that we could work through this as well. So this is a to the 7th plus 7, a to the 6th b, plus 21 a to the 5th b squared, plus 35 a to the 4th b cubed, plus 35 a cubed b to the 4th, plus 21 a squared b to the 5th, plus 7 a b to the 6th, plus b to the 7th. Well, what do we know? Well, now we know a is 3 to the x, b is 2y. So now we can just plug into that to get our equation. So this would be, and I'm going to run out of room here, but I'm going to try and get all this on here. So this would be a to the 7th. Well, that's 3x to the 7th plus 7 times 3x to the 6th times 2y plus 21, 3x to the 5th, 2y to the squared plus 35. A is 3x to the 4th, 2y to the 3rd plus 35, 3x to the 3rd, 2y to the 4th plus 21, 3x squared, 2y to the 5th plus 7, 3x, 2y to the 6th plus 2y to the 7th. So now we need to go through and just multiply out those coefficients to get all those terms. And when you do that, you're going to get some big numbers. This is what you should get. 2187 x to the 7th plus 10206 x to the 6y plus 20412 x to the 5th y squared plus 22680 x to the 4th y cubed plus 15120 x cubed y to the 4th plus 6048 x squared y to the 5th. Go ahead and pause the video and see if you can get letter A and letter B. And here we go. So we can use our pattern. This is x to the 8th plus 8 x to the 7th y. 8 times 7 is 56 divided by 2 is 28 x to the 6th y squared. 28 times 6 divided by 3 is 56 x to the 5th y cubed. 56 times 5 divided by 4 is 70, and that's x to the 4th y to the 4th. That's the middle because the exponents are the same. Now we're repeating 56 x to the 4th, x to the 3rd y to the 5th plus 28 x squared y to the 6th plus 8 x y to the 7th plus y to the 8th. Letter B, we're going to do the same thing as we did up above. We're going to find our pattern first, and our pattern is going to be to the 7th. And so that is, if we call A is 1, B is -5, y, A is 1x. So I'm going to do this in terms of A to the B, and then we'll plug in A's. So this is A to the 7th plus 7, A to the 6b. And after a while, you'll notice we actually have most of these examples in here. So we've done everything from 5. We haven't done 6, although there's 6 right there. There's 7, there's 8. So you have a lot of reference to go back when you're looking at your homework. A to the 6b plus 21, a fifth b squared plus 35, a to the 4th b cubed plus 35 a cubed b to the 4th plus 21 a squared b to the 5th plus 7 ab to the 6th plus b to the 7th. Now we're going to plug in what we know, and that's going to be x to the 7th plus 7 times x to the 6th negative 5y plus 21 x to the 5th negative 5y to the 2nd plus 35 x to the 4th negative 5y to the 3rd plus 35 x cubed times negative 5y to the 4th plus 21 x squared negative 5y to the 5th plus 7x negative 5y to the 6th plus negative 5y to the 7th. Now we need to go back and simplify all of that by multiplying out the coefficients. The variables stay the same, and we get for our final answer x to the 7th minus 35 x to the 6th y plus 525 x to the 5th y squared minus 4375 x to the 4th y cubed plus 21 875 x cubed y to the 4th minus 65 625 x squared y to the 5th, almost there, plus 109,375 x cubed y to the 6th minus 78125 y to the 7th. How are we going to use this? Example, of the 7 children born to the Macaulays, at least 3 are boys. How many of the possible boys and girls have at least 3 boys? So if you have a kid, what's the possibility? Well, either you're going to have a girl or a boy. They have 7. So what are the possibilities? Well, that's a binomial expansion. So let's walk through this. So you could have 7 girls. There's one way you could have 7 girls is what this means. There are 7 ways you could have 6 girls and 1 boy. There are 21 ways you could have 5 girls and 2 boys. There are 35 ways to have 4 girls and 3 boys. There are 35 ways, and by ways I mean in order in which they're born, right? If you have all 7 girls, there's only one way to get all 7 girls. They're all girls. If there's 7 ways to get 6 girls and 1 boy, because a boy could be 1st, 2nd, 3rd, 4th, 5th, 6th, or 7th. So we're looking at all the different methods, all the different ways that they could be in birth order. 35 girls, 3 girls, and 4 boys, plus 21 ways you could have 2 girls and 5 boys, plus 7 ways to have 1 girl and 6 boys, and only 1 way to have 7 boys. We want to see how many of the possible groups of boys and girls have at least 3 boys. So what does it mean to have at least 3 boys? That means there are 3 or more boys. And that would be b cubed. So we're looking at these. So that's the 35 plus the 35 plus the 21 plus the 7 plus the 1, which is 99, over the total. So add in the 21, the 7, the 1, that's 128. And that gives us a percentage of the likelihood that they would have, if they had 7 kids, that they'd have at least 3 boys. That would be a 77%. Now, again, that's assuming that it's a 50% split on the chance of having a boy or a girl. We're going to skip checkpoint 2. We can generalize, and this is what Pascal came up with. He said that there's an easier way to generalize the binomial theorem. And that is to use this thing, the binomial formula. And here's the binomial formula. X plus y sub n, the thing we've been working with, is the same as the summation from r equals 0 to n of this formula, n factorial over r factorial times n minus y factorial to x to the n minus r, y to the r. And we're going to write that another way. And we're going to write that as Now I can't remember if that's a permutation or a combination. Summation of r equals 0 to n. And if I remember correctly, that's n choose r. And remind me in class, we need to clarify if that's right or not. And so let's use the binomial theorem to expand. So to the 6th power, this means we have the sum of r equals 0 to 6 of 6 factorial over r factorial 6 minus r times 2x, that's our first term, to the 6 minus r, y to the r. So let's see what happens when we plug in r equals 0, 1, 2, 3, 4, 5, and 6. So that gives us 6 factorial over 0 factorial, which is actually 1, times 6 minus 0 factorial, times 2 to the 6 minus 0, negative 1 to the 0. And that is our coefficient. We end up with 64. The variables all work the same, so I'm not going to worry as much about the variables. But basically the way this formula works is we're counting down. So if r is 0, then we're counting down. It's 6 and 0. 1 would give us 5 and 1, and then 4 and 3. So it's a way to count down with the x, a way to count up with the y. So we get x to the 6th. We can keep doing that, and we get this number. So this is a better way. If we want just one term, we don't have to generate the whole pattern. So we can use our formula to get just specific terms without having to do the whole sequencer series. Again, in class, I'll show you another way that we can do this as well. For example, find the 5th term of a to the 4 plus 3b to the 7. So n is equal to 7. We want the 5th term. So if we want the 5th term, what's r? That's our question. Remember, we're starting to r equals 0. So that means we have to go down 1. So r here, we actually want 4 to get to the 5th term. You have to consider 5 minus 1 to get r equals 4. We're using our formula n factorial over r factorial n minus r factorial times x to the n minus r over y to the r. That gives us 7 factorial over 5 factorial, because we want the 5th term. N minus r then would be 3 factorial times 4. Now we want 6 minus r is 3, and 3 to the 4th. And so the 5th term should be 4a plus 3b to the 7th. And if we do all that multiplication, we get 181,440 a cubed b to the 4th. Again, remind me in class, we'll look at other ways to do this with your calculator. Here's our homework, last homework section for chapter 12, page 804. We're doing 6 through 30 evens. Have a good day, Maroons.